This is the fifth video of a fourth complex number series on de Moivre's theorem for OCR Pure Core Further Mathematics, and it looks at finding multiple angle identities using de Moivre's theorem. You should already be familiar with these trigonometric identity and compound angle formula, as they are part of the second half of the A-level maths syllabus. However, if you're not, please do go and look them up. Here we are asked to use de Moivre's theorem to show that cos 4 theta equals cos to the power 4 theta minus 6 cos squared theta sine squared theta plus sine to the power 4 theta, and sine 4 theta equals 4 cos cubed theta sine theta minus 4 cos theta sine cubed theta. We could obtain these results without using complex numbers, but it takes much more effort. Please note that I'll be using C to represent cos theta and S for sine theta, partly to save space, but it is also a common convention that you may find in textbooks or online. I will also be using Pascal's triangle to coefficients in expansions. For example, expanding for power 4 leaves me to coefficients 1, 4, 6, 4 and 1. Let me start by considering the expansion of cos 4 theta plus I sine 4 theta. In fact, it equals cos theta plus I sine theta to the power of 4 using de Moivre's theorem. So expanding that second bracket, I would get C4 plus 4i C3s plus 6 minus 1, which is I squared, C squared S squared, plus 4 minus I, given that I cubed is the same as minus I, C S cubed, plus 1, this being the same as I to the power 4, S4. I can now easily equate the real and imaginary parts. So for the real part I had cos 4 theta. And picking the real elements out of the expanded expression above, I can see that that is C4 minus 6 C squared S squared plus S for 4. For the imaginary, that is my S 4 theta or sine 4 theta will equal 4 C cubed S minus 4 C S cubed. Remembering that the C stands for cos theta and the S for sine theta. If I was to write those out in full, you would indeed see that that was what I was asked to prove. Sometimes it is useful to do the reverse, particularly if you want to integrate a power of cos theta or sine theta. Reminding ourselves that z to the n using de Moivre's is cos n theta plus I sine n theta, while z to the minus n is cos n theta minus I sine n theta. We can see that if we add z to the n and z to the minus n, then the I sine theta terms will cancel out, and this leads to cos n theta equals z to the n plus z to the minus n over 2. Subtracting would lead to the cos theta cancel out, and this would lead to sine n theta equal to z to the n minus z to the minus n over 2i. These are useful results that we will see again in later videos. So let us express sine cubed theta in terms of multiple angles. I'm going to use sine theta times 2i equals z to the 1 minus z to the minus 1. And here n equals 1 in this formula down here. If I raise that to the power of 3, I would have 2 cubed I cubed sine cubed theta equal to z minus z to the minus 1, all cubed. This would give me 8 minus I sine cubed theta equal to z cubed minus 3z plus 3z to the minus 1 minus z to the minus 3. And I've used Pascal's triangle to find those coefficients 1, 3, 3, 1. I can regroup those as being z cubed minus z to the minus 3 minus 3 lots of z minus z to the minus 1. And you can see that again I can use that formula with n equals 1 and n equals 3 to rewrite that as 2i sine 3 theta minus 6i, because of that factor of 3, sine theta. Dividing by that minus 8i and rearranging then leads me to sine cubed theta equals 3 sine theta minus sine 3 theta over 4. And I have therefore expressed sine cubed theta in terms of multiple angles. This is the final video of the fourth complex number series.